In the silence between worlds, something has entered our solar system again. Astronomers first thought it was just another comet faint, unremarkable, another streak in the endless catalogue of moving dots. But as it drew closer to Mars, the data began to shift. Instruments flickered, magnetometers pulsed. And then, for reasons no one could fully explain, the red planet itself seemed to answer back. Designated 3I Atlas, this interstellar traveller is only the third object ever known to come from beyond our sun's gravity. Yet its passage has done something none of the others did. It triggered measurable changes on Mars. What exactly happened out there, 40 million miles away, is still unfolding. But one thing is clear. 3I Atlas didn't just pass through our solar system. It left a fingerprint, the discovery that shocked astronomers. It began quietly in the last weeks of 2024, when a faint moving dot appeared in the nightly scans of the Asteroid Terrestrial Impact Last Alert System, better known as ATLAS, operating out of Hawaii. The telescope, designed to spot incoming threats to Earth, had seen thousands of near-Earth objects before, but this one was different. It was moving far too fast and at an odd trajectory that didn't fit the pattern of any known solar system body. Initial calculations suggested it was inbound from the direction of the constellation Lyra on a hyperbolic orbit that would take it straight through the inner solar system and past Mars within a matter of months. The data was sent automatically to the Minor Planet Center in Cambridge, Massachusetts, and soon astronomers around the world began following the track. Within hours, the new visitor was given a temporary designation, 3I Atlas, the third confirmed interstellar object ever detected after 1I, Oumuamua, in 2017, and 2I, Borisov, in 2019. At first, few outside the small community of Comet researchers noticed. The object was faint, about magnitude 19, and the images looked unremarkable. Yet when spectra from the Nordic Optical Telescope in La Palma came back, they revealed a curve unlike any previously recorded for a comet or asteroid. The reflected light showed an unusual dominance of cyanide and carbon chains, but the relative absence of water ice. That suggested a surface baked and weathered by long exposure to interstellar radiation. It's like something that has been drifting between stars for eons, said Dr. Karen Meach of the University of Hawaii's Institute for Astronomy, who also studied Oumuamua. We're looking at material older than the solar system itself. When the European Space Agency's Near-Earth Object Coordination Center ran the orbital simulations, they discovered a surprise. Instead of simply skimming through the system, 3I Atlas would pass close enough to Mars, roughly 0.14 astronomical units, or about 21 million kilometers, to interact with the planet's thin magnetic tail. That encounter, expected around July 2025, could provide an unprecedented natural experiment. What happens when interstellar material brushes against a planetary magnetosphere? Both ESA's Mars Express and NASA's MAVEN spacecraft were quietly scheduled to collect data during the passage. As the days passed, amateur astronomers began to confirm the object's acceleration. Its non-gravitational motion hinted at outgassing, yet no visible coma had appeared. On social media, scientists exchanged theories. Was it tumbling irregularly, like Oumuamua? Could outgassing jets be hidden beneath a crust of carbon compounds? Or was something else producing the acceleration solar radiation pressure acting on an extremely light, porous structure? The debates were civil but intense. In January 2025, the International Astronomical Union officially confirmed the hyperbolic nature of its path, assigning it the permanent designation 3I Atlas C 2024, a 3. The object's eccentricity, 1.16, placed it firmly in the interstellar category. What made 3I Atlas so compelling was its timing. Humanity's instruments were better prepared than ever before. The James Webb Space Telescope could peer into its dusty coma. Hubble could track the reflected light, and a fleet of Mars orbiters offered an array of sensors waiting for its flyby. On the 11th of February 2025, NASA's Planetary Defense Coordination Office released an updated bulletin. The comet was brightening faster than models predicted, possibly due to increased solar heating as it approached the inner system. By March, astronomers at Lowell Observatory in Flagstaff, Arizona, noted an unusual asymmetry in the coma's formation, a filamentary structure extending away from the Sun at an angle inconsistent with normal solar wind flow. The discovery paper, published in the Astrophysical Journal Letters, described it as a dynamic, rotating plume of dust and ionized gas with variable brightness. Meanwhile, the Mars science community began preparing for something extraordinary. MAVEN's principal investigator, Bruce Jakosky, circulated an internal memo warning that the interstellar object could induce temporary changes in Mars's magnetotail plasma density. We might witness an interstellar particle stream interacting with a planetary environment for the first time, he wrote. To capture it, the spacecraft would increase its telemetry rates in late June and coordinate with Mars Express's Aspra-3 instrument. Even China's Tianwen-1 mission quietly adjusted its observation schedule. By April, ground observers were reporting the comet visible through small telescopes in the southern hemisphere with a greenish tinge characteristic of diatomic carbon. Yet photographs revealed faint linear anomalies near the coma, tiny streaks that moved in concert with 3I Atlas but weren't optically connected. The discovery came from astrophotographer Michael Jaeger in Austria, who had captured similar phenomena around 2.1 Borisov years earlier. This time, however, the number of secondary streaks increased week after week. We're seeing a swarm of fragments, or perhaps dust sheets, travelling alongside it, said Dr. Jessica Agarwal of the Max Planck Institute for Solar System Research. Theories ranged from normal fragmentation to the idea of pre-existing interstellar debris following similar trajectories. Either way, something unusual was unfolding. When May 2025 arrived, major observatories from Chile to Japan were training their instruments nightly. The comet's activity surged as it reached 1 AU from the Sunday. Unexpected ultraviolet spikes detected by MAVEN suggested bursts of ionized carbon at levels far above normal cometary output. A faint increase in the Martian upper atmosphere density was logged days later. The coincidence intrigued scientists. Could dust or gas from an interstellar object actually influence the planet's aeronomy? Though the amounts were minuscule, it was enough to raise eyebrows. Mars is effectively our early warning laboratory, one researcher remarked during an online ESA panel. What happens there could inform how interstellar material interacts with any planet, including Earth. As 3I Atlas swept inward, its faint tail lengthened to nearly 3 degrees across the sky. Amateur observers described it as ghostly, almost artificial in shape. The comet's core brightened and faded irregularly, suggesting rotational instability. Then, in early June, the Jet Propulsion Laboratory released a statement confirming a brief outburst event, an energy release equivalent to several kilotons of TNT that momentarily increased its brightness by a factor of 50. The origin of the outburst remains under analysis, but the timing weeks before the Mars flyby ensured that every instrument near the red planet would be watching. By mid-June, as the object continued its approach, an uneasy sense of anticipation spread through the astronomy community. The event would be historic regardless of outcome, a direct encounter between another system's debris and the Martian environment. "We're about to observe a piece of another solar system passing through ours," noted Dr. Meach during an interview with Nature Astronomy. That's never going to be ordinary. The instruments turned toward Mars. In early July 2025, the attention of almost every major planetary science mission converged on one point in space: the corridor through which 3i Atlas would pass behind Mars. NASA's MAVEN, ESA's Mars Express, China's Tianwen-1, the United Arab Emirates Hope Orbiter, and even NASA's aging Odyssey were ordered to coordinate telemetry, sharing plasma, ultraviolet, and dust particle data in real time. For the first time since the arrival of the Perseverance rover, every eye, optical and electronic, was turned not toward the Martian surface, but toward its sky. Inside the MAVEN operations room in Boulder, Colorado, mission planners had prepared a sequence labeled Atlas Track Set 05. It reprogrammed the spacecraft's magnetometer to higher frequency sampling and altered its periapsis timing so that each orbit would skim the tail of Mars's induced magnetosphere during the comet's closest approach. "We're treating it like a controlled laboratory," project scientist Shannon Curry explained in a NASA press call. "Whatever particles are coming in, we'll catch them." Engineers at ESA performed a similar update for Mars Express, reactivating the long-dormant Aspera 3 instrument, built to detect charged ions and solar wind interactions. After 17 years of near standby duty, Aspera 3's sensors would once again register Martian plasma and perhaps something foreign within it. On the 7th of July 2025, the first indication of anomaly arrived. MAVEN's magnetometer recorded a faint but distinct oscillation in the planetary tail, roughly 30 minutes after a solar wind lull. The waveform's period was 2.3 minutes too long for typical plasma waves, too short for atmospheric tides. Analysts compared it to background data stretching back years and found no precedent. 2 hours later, Mars Express detected a correlated spike in ion flux moving in the opposite direction of the solar wind. The coincidence suggested an external driver, not an internal planetary process. NASA confirmed that 3i Atlas was, at that exact time, 23 million kilometers from Mars, and crossing a region magnetically connected to the tail. "It was like a subtle tap on the magnetosphere," said Dr. Curry. Something had brushed past the field lines. Over the next 48 hours, as the object approached its point of closest passage, the signals intensified. MAVEN's magnetometer showed quasi-periodic pulses every 6 hours, aligning closely with the spacecraft's orbital precession. The Hope orbiter recorded transient ultraviolet auroras above the northern hemisphere. Faint, but measurable. Mars had displayed auroral activity before, caused by solar storms, but there had been no solar flare, no coronal mass ejection. The only variable was the incoming interstellar visitor. "We're witnessing an interaction that's neither cometary nor planetary," noted French astrophysicist Jean-Yves Chauffret, whose team monitored the emissions from Meudon. "It's a new category altogether." As July 10 approached, astronomers on Earth reported unexpected dimming in the comet's brightness curve. The decline wasn't uniform. Instead of fading smoothly, 3i Atlas flickered erratically, as if veiled by transient clouds. The Vera C. Rubin Observatory in Chile recorded 4 discrete dips, separated by roughly 12 hours each. Planetary scientist Dr. Anita Cochrane proposed that the fluctuations might correspond to rotation combined with ejection events, shedding fragments invisible to direct imaging. Yet, when the James Webb Space Telescope pointed toward it on July 11, its mid-infrared detectors revealed no significant thermal spikes, only a cool, diffuse object with an unexpectedly flat temperature gradient across its surface. The absence of hotspots suggested minimal outgassing. "It's cold, inert, and still somehow interacting," she remarked. At 3:17 UTC on July 13, MAVEN crossed the night-side magnetotail just as 3I Atlas reached minimum distance, roughly 20.9 million kilometers. The spacecraft's solar wind ion analyzer registered a sudden influx of high-energy carbon ions at velocities exceeding 60 kilometers per second, a clear outlier from solar origin. Within minutes, the Mars Express radio science team reported brief phase disturbances in its X-band link, lasting 7 seconds. The disruptions were too short for a hardware fault and occurred simultaneously at 2 tracking stations, Cebreros in Spain and New Norcia in Australia. Later, the data analysis would reveal a sharp, narrowband interference centered at 8.42 GHz, coincidentally near the natural emission line of 4-mile radicals, HCO. Whether that alignment meant anything physical or was simply chance remained uncertain, but it added to the growing sense that 3I Atlas was not behaving like an ordinary comet. Meanwhile, on the Martian surface, the Perseverance rover's cameras captured a series of faint, slow-moving streaks across the twilight sky. The streaks lasted less than 2 seconds each, moving almost parallel to the horizon. When correlated with orbital timing, they aligned with micrometeoroid entries, dust grains only millimeters across, arriving from the inbound direction of 3I Atlas. These were the first physical particles of interstellar material ever documented entering a planetary atmosphere. Although each grain burned harmlessly in the thin air, spectroscopy from the SuperCam instrument showed elevated magnesium and silicon ratios distinct from known Martian meteoroids. For a few minutes, said mission scientist Roger Wiens, Mars was literally under interstellar rain. By July 14, the comet had passed perihelion and was already receding from Mars's orbit, yet the anomalies persisted. MAVEN's magnetometer continued to detect quasi-periodic pulses for another 48 hours before fading back to baseline. Scientists debated whether residual plasma or electromagnetic induction could account for it. Others cautioned that the spacecraft might be detecting its own feedback from charged dust. Still, none could explain why the same pattern appeared across multiple instruments, each built by different agencies and operating independently. On July 15, NASA's Deep Space Network recorded the final direct telemetry burst from MAVEN's high-gain antenna before the spacecraft entered safe mode to preserve power. In that last data packet lay something puzzling, a transient voltage spike in an auxiliary sensor not meant for science use. It lasted 0.7 seconds and occurred precisely as the comet's tail crossed the line between Mars and the Sunday. Engineers later traced it to the spacecraft's static discharge monitor, a device designed to warn of electrostatic buildup. The reading implied a brief, external electromagnetic pulse. "We don't know what caused it," admitted NASA's flight director Tom Casper during the post-event briefing, but it coincided with the final moment of the encounter. When operations resumed, Mars's environment had returned to normal. The red planet spun quietly beneath a thin veil of dust. Solar winds flowed undisturbed, and 3I Atlas receded into the darkness beyond. But the gigabytes of data stored across those missions told a subtler story of fields trembling, particles accelerating, and light dimming in ways that no model had anticipated. The world's scientists were only beginning to piece together what exactly had brushed the edges of Mars, the data that wouldn't fit the models. When 3I Atlas cleared the Martian orbit in mid-July 2025, it left behind a mountain of raw numbers, terabytes of telemetry from more than half a dozen spacecraft. Every agency involved began its own analysis, expecting to confirm a routine electromagnetic interaction. Instead, they encountered results that refused to align with any known plasma or comet model. At NASA's Goddard Space Flight Center, MAVEN data analysts worked around the clock, comparing the July magnetometer traces with control runs from earlier in the year. The amplitude of the oscillations had decayed too slowly. The plasma density in the magnetotail should have normalized within hours of the object's departure, yet it lingered for days. It's as if something continued to resonate after the trigger was gone, said Dr. Daniel Luhmann, a veteran space physics researcher. When the waveforms were decomposed using Fourier analysis, they revealed nested harmonics frequencies spaced in a geometric sequence rather than the usual random spread. That pattern had never been seen in the Martian environment before. ESA's Mars Express team found their own puzzle. The Aspera 3 instrument recorded ion energies skewed toward heavy carbon clusters, C4-MISE, C6-MISE, C8-MISE ratios, typical of interstellar organic dust, not solar wind ions. We're seeing complex carbon fragments that shouldn't survive the trip from interstellar space intact, reported Swedish physicist Stas Barabash, one of Aspera 3's original designers. The data implied that the grains were either shielded or somehow regenerated during interaction. When cross-checked against MAVEN's neutral gas and iron mass spectrometer, both datasets showed identical energy peaks at 54 and 108 electron volts, precisely double one another. The correlation was too clean to be noise. On Earth, radio astronomers at the Square Kilometre Array in South Africa detected narrow-band emissions from the comet's path even after it had moved beyond Mars. The signal hovered around 8.42 GHz, the same frequency blip noted in Mars Express telemetry. At first, they assumed ground interference, but the signal followed the object's predicted trajectory across the sky and faded only when it crossed behind the Sunday. It's a natural emission line, argued Dr. Eleanor Singh of the SKA team, but the coherence length is bizarrely long for a diffuse tail. The idea that a comet could act as an interstellar maser amplifying microwaves was floated in several internal memos but never formally published. In Pasadena, JPL's radar scientists compared archival observations from Goldstone with the latest optical data. They found minute deviations in the object's spin rate, a slowdown of 0.6% following the peri-Martian passage. That might sound trivial, yet given the comet's size, roughly 800 meters across it, implied a torque unaccounted for by gas jets alone. The deceleration vector points opposite to the magnetotail direction, one engineer noted. That's not solar radiation pressure. It's as if the field interaction itself applied drag. The finding reignited debates about whether charged dust interacting with planetary magnetic fields could impart measurable momentum to passing bodies. In late July, NASA convened a joint teleconference with ESA, CNSA, and the United Arab Emirates Space Agency. The agenda: consolidate all data related to the 3I Atlas event. The transcript, later released under FOIA, showed confusion but no drama. Representatives agreed to publish a unified timeline, yet behind the scenes, specialists from multiple universities began forming small working groups to rerun the plasma models. Dr. Luhmann's team discovered that only by introducing an additional parameter, a transient magnetic loop lasting about 12 hours, could the magnetometer data be replicated. The source of that loop remained unidentified. Meanwhile, planetary geologists reviewing Perseverance's atmospheric spectra noticed something subtle. During the nights of July 13 to 14, when the interstellar rain was recorded, the rover's spectrometer showed a temporary enrichment in isotopic carbon-13 within the CO2 column. The variation was tiny, about 0.08%, but statistically significant. The enrichment disappeared 2 sols later. If interstellar carbon grains ablated in the upper atmosphere, that's exactly the isotopic signature we'd expect, said Dr. Paul Mahaffey, formerly of NASA's SAM experiment on Curiosity. It meant that a measurable quantity of alien material had briefly merged with Mars's air. By early August, the comet's distance from the Sun had increased beyond 1.5 AU, yet its light curve refused to fade. The Subaru telescope on Mauna Kea observed a persistent luminosity plateau consistent with ongoing activity at low solar input. Such behavior contradicted standard sublimation theory. Some suggested that the dust particles trailing it were photoluminescent, re-emitting absorbed ultraviolet energy over time. Others pointed to possible electrostatic charging from the Martian interaction that kept the coma glowing long after solar heating should have waned. At a press briefing on the 12th of August 2025, NASA's Planetary Science Division released a cautious statement. Preliminary data indicate that 3I Atlas exhibited anomalous interactions with the Martian magnetosphere and atmospheric environment. The phenomena are under active investigation. No one called it unprecedented, but the implication hung in the air. For the first time, an interstellar object had measurably affected another planet's electromagnetic field and possibly its upper atmosphere. Outside the official channels, independent researchers began mining public datasets. Amateur analyst Alexei Voronin from Novosibirsk plotted the timing of Maven's pulses against the comet's rotational period inferred from photometry. The ratios matched within 2%, hinting that the magnetic oscillations might have been modulated by the object's own spin. If the core carried remnant magnetization, even a weak one, it could couple with Mars's induced field, he wrote in an online preprint. Within days, the paper was circulating through research Slack channels, drawing cautious interest. By September, the flood of observations had become a thicket of contradictions. Plasma physicists insisted the disturbances were natural. Chemists pointed to exotic organic signatures. Radio astronomers debated the 8.4 GHz mystery. A pattern seemed to emerge, something more organized than random debris, but less than deliberate action. It's a relic, not a messenger, wrote one European researcher. A frozen witness of another system's chemistry colliding with ours. Whatever 3I Atlas truly was, it had left Mars's neighborhood humming with questions that no instrument could yet silence. The swarm behind the comet. By late September 2025, the scientific focus shifted from 3I Atlas itself to what it had left in its wake. Ground-based images from Chile's Paranal Observatory and Japan's Subaru telescope revealed a strange structure in the dust tail, a collection of discrete luminous knots travelling along nearly parallel paths. Each knot maintained a consistent velocity relative to the main nucleus, as though a convoy of tiny bodies were escorting it through space. The phenomenon reminded astronomers of the fragment trails left by comets that have undergone nucleus splitting, yet none of the brightness profiles matched standard fragmentation models. Every fragment seems too stable, too coherent, remarked Dr. Masato Ishiguro of Seoul National University, who had earlier studied 332P Ikea Murakami's breakup. These are not random shards, they're organized. Spectroscopic analysis from the Lowell Observatory confirmed the fragments were reflecting sunlight at slightly different wavelengths, a subtle gradient from blue-white to greenish, suggesting variable particle size, or composition. When researchers modelled their orbital dynamics, they discovered that the fragments formed a shallow arc, a structure unlikely to result from explosive ejection. Instead, the geometry pointed to sequential shedding over several weeks, possibly driven by internal stresses. The timing aligned perfectly with the object's closest approach to Mars. One theory gained quiet traction. Electromagnetic coupling with the planet's magnetotail might have induced surface fracturing, peeling layers from the nucleus like flakes from a drying lakebed. On October 1, the European Space Agency's Near-Earth Object Coordination Center released updated tracking data. At least 19 distinct sub-objects now accompanied 3I Atlas, each between 10 and 50 meters across. Their albedos were higher than expected, hinting at freshly exposed material. In infrared, the James Webb Space Telescope detected none of the usual thermal signatures of sublimating ice. Instead, the fragments emitted a flat, featureless spectrum consistent with carbon silicate glass. Dr. Heidi Hamel, part of JWST's solar system team, called the material optically dark, thermally quiet, like vitrified ash. As the swarm moved outward beyond 1.7 AU, Earth-based radar attempted a ping using NASA's Goldstone dish. The return was faint but unusual. The echo strength fluctuated at regular intervals, as if the target cross-section was modulated by rotation or internal layering. Analyst John Giorgini described it as a comb pattern, peaks and troughs spaced too evenly to be noise. In a follow-up email obtained by Science magazine, he speculated that the fragments might be loosely bound clumps carrying residual charge, slowly repelling one another under electrostatic forces. No one could confirm it, yet the idea fit the data better than gravity alone. Meanwhile, amateur observers contributed critical context. In Australia, astrophotographer Michael Matiazzo used a custom-built 0.25-meter telescope with a high-speed CMOS camera to record the tail over several nights. When he stacked the frames, faint ripples became visible wave-like oscillations travelling along the dust stream. Measured over time, their wavelength shortened as the comet receded. Matiazzo posted the findings to an online forum where professionals quickly joined the discussion. The consensus was that these were density waves propagating through the charged dust field, possibly remnants of the electromagnetic disturbance first seen near Mars. By mid-October, the swarm had begun to diverge. Several of the smaller fragments drifted ahead of the nucleus, while others lagged behind, forming a loose envelope nearly 300,000 kilometers long. At Palomar Observatory, a photometry team led by Dr. Jules Henderson detected synchronized flickers among 3 of the body's brief, brightening events, repeating every 4 hours. The rhythmic pattern suggested rotation rates locked to a shared period. In natural fragmentation, spin rates vary wildly. Synchronization implied coupling, perhaps through mutual charging or dust-plasma interactions. It's like they're still connected by invisible threads, Henderson noted. NASA's Planetary Defense Coordination Office published an interim bulletin warning that the fragment trajectories intersected the orbital plane of Mars once more in February 2026. The fragments were too small to pose danger, but their persistence meant they could act as tracers for understanding interstellar dust dynamics. Plans were drafted for MAVEN and Mars Express to resume high-sensitivity observations during that window. At JPL, simulations predicted that the densest portion of the debris field would cross 0.02 AU inside Mars's orbit, providing another chance to sample alien material. In parallel, chemists examined the peculiar reflectance spectrum recorded during the object's closest approach. The pattern showed sharp absorption lines at 388 and 431 nanometers regions associated with cyanogen and diatomic carbon. but with an added shoulder near 420 nanometers that didn't correspond to any common molecule. When laboratory astrophysicists at Heidelberg recreated the mixture under vacuum ultraviolet radiation, they found the extra feature appeared only when carbon dust was infused with iron-nickel nanograins. Such composition would imply the object once originated from a system rich in metallic debris, perhaps the outer remnants of a supernova-polluted disk. If true, said Dr. Anja Falk of the Max Planck Institute, we're literally sampling the ashes of another star's planetary formation. The press seized on that poetic phrasing, but most scientists remained cautious. Still, a quiet sense of awe pervaded the community. Interstellar visitors were rare enough, one that fragmented, interacted, and lingered long enough to study in detail was unprecedented. At Caltech, dynamical modeler David Farnokia recalculated the orbital solution using the latest data and noted a minute but consistent deceleration unaccounted for by gravity or outgassing. When plotted over time, the slowdown followed an exponential curve identical to the fading of the magnetotail pulses detected months earlier. Two independent phenomena, thousands of kilometers apart, seemed to share one mathematical fingerprint. By October 20, telescopes in both hemispheres reported the first clear signs of dissipation, the nucleus dimmed by half a magnitude, and the swarm's leading fragments blurred into a continuous band. Yet radio observatories continued to receive weak, narrowband emissions at 8.42 GHz, fainter now, but still synchronized with the comet's rotation period. For months, the emission would persist like a heartbeat from the edge of the solar system, a fading reminder of the encounter that had turned Mars into an unintended experiment. As data kept flowing, researchers realized they had stumbled upon something more complex than a passing visitor. The remnants of 3I Atlas were behaving like a self-organizing system, bound not by gravity, but by charge, magnetism, and memory, an echo of forces forged in another sun's domain, now weaving their patterns across ours. The race to decode the signal. By late October 2025, the persistent 8.42 GHz emission trailing 3I Atlas had become the centerpiece of a scientific race. What began as a faint line in the background noise of Mars Express telemetry was now being tracked by half the world's radio telescopes. The frequency sat just above the hydroxyl line and below common spacecraft bands too precise to dismiss, too narrow to ignore. The Jet Propulsion Laboratory confirmed it originated from the same region of space occupied by the receding swarm of fragments. "It's not an artifact," insisted Dr. Eleanor Singh during a teleconference at Caltech. "Whatever is producing this has coherence. It's acting like a natural maser. The Square Kilometre Array in South Africa and the Atacama Large Millimetre Array in Chile coordinated nightly observations. The emission pulsed faintly every 9 hours, matching the rotation period of the remaining nucleus. Each burst rose and fell within seconds, repeating with mechanical precision. Spectral decomposition showed sidebands at plus or minus 22 kHz, suggesting modulation, something unheard of in cometary physics. The simplest explanation, a Doppler wobble caused by spin, failed when the phase shift remained constant through multiple rotations. That left only two options: some unknown physical process or interference from a structured field within the tail. In November, ESA's Operations Center authorized Mars Express to turn its high-gain antenna toward the source for a passive listening experiment. Over a 48-hour window, the spacecraft captured 15 bursts. When decoded into waveform plots, the signals displayed a curious envelope, a sawtooth rise followed by a linear decay, like a heartbeat on a monitor. Engineers ruled out internal oscillators, and solar interference. The timing coincided with the densest portion of the fragment swarm crossing 1.9 AU from the Sunday. To verify, NASA enlisted the Deep Space Network's Canberra complex to record at the same frequency. The same pattern appeared again, identical timing, identical shape. 2 independent receivers, 2 hemispheres, 1 source, read the internal report. Speculation rippled through the astrophysics community. Some invoked stimulated emission in ionized carbon clouds, essentially a natural laser produced by the charged debris. Others argued for magneto-hydrodynamic resonance between the fragments. The more conservative explanation held that oscillating plasma currents within the coma could mimic modulation without intelligence. Yet the symmetry was hard to ignore. In an interview with Nature Astronomy, Dr. Heidi Hammel cautioned, "Pattern does not equal purpose, but pattern demands explanation." Meanwhile, the political dimension grew. A classified memo leaked from the European Space Policy Office indicated that several national defense agencies had requested early access to the raw signal data, citing spectral overlap with critical communication bands. The United States, Russia, and China filed similar requests through diplomatic channels. To prevent speculation from spiraling, NASA, ESA, and CNSA announced a joint open data initiative, Project Atlas, dedicated to releasing every unprocessed observation of the interstellar object to the public within 60 days. The unprecedented collaboration was meant to reinforce transparency, but it only amplified attention. When the first datasets appeared online in mid-November, thousands of independent analysts downloaded them. Amateur radio astronomers built backyard parabolic dishes to replicate the detection. Within days, confirmed receptions poured in from Spain, Argentina, and Australia. The 8.42 GHz line was real, though faint, so faint that any random fluctuation could drown it. Still, its persistence over weeks intrigued professionals. JPL's signal processing team applied autocorrelation analysis and found a repeating interval of 33 minutes embedded within the broader 9-hour cycle. The sub-pulse pattern remained stable for 20 rotations before drifting. No terrestrial transmitter shows that behavior, one analyst noted. If it's natural, it's new. By December, as 3i Atlas crossed 2 AU outward, the signal began to weaken. Yet in its dying moments, it changed character. The sidebands collapsed, leaving a pure tone that faded exponentially, as if the source were cooling or discharging. For radio astronomers, it was the equivalent of hearing a dying star exhale. The last clear detection came on the 18th of December 2025, recorded simultaneously by dishes in Effelsberg, Germany, and Parkes, Australia. Then the line vanished into cosmic static. In the aftermath, labs across the world compared notes. Plasma physicists proposed that the fragment's carbon silicate surfaces, charged by the Martian magnetotail, could have created resonant cavities amplifying microwave emissions until the charge dissipated. Chemists countered that iron-nickel inclusions detected by JWST might have acted as natural antennas, focusing radiation. The argument remained unresolved. "Nature can organize itself into extraordinary order," said Dr. Singh in a December press conference. But 3i Atlas organized it at a scale we didn't expect. As winter deepened on Earth and the interstellar traveler slipped toward the darkness beyond Jupiter's orbit, the tone at observatories turned from excitement to reflection. The data were real, the cause remained elusive. In its brief passage, 3i Atlas had connected planets, agencies, and disciplines in a shared puzzle stretching from Hawaii to Mars. The signal that once hummed through the void now existed only in archived waveforms, mathematical fossils of a conversation no one fully understood. the Project Atlas Coalition. The official launch of Project Atlas on the 6th of January 2026 marked the first truly global scientific consortium devoted to a single interstellar event. More than 200 institutions from 40 nations signed the framework agreement, pledging to pool all raw data, algorithms, and observation schedules related to 3I Atlas. The headquarters was established in Geneva, a symbolic midpoint between NASA's Jet Propulsion Laboratory and the European Space Agency's Operations Center in Darmstadt. From a glass-walled control room overlooking Lake Geneva, data streams from space-based and terrestrial observatories converged in real time, processed by servers humming 24 hours a day. Dr. Karen Meach, who had first characterized Oumuamua 8 years earlier, was appointed scientific chair. Her opening statement set the tone. "We are not investigating anomalies. We are documenting a natural event that challenges what we call natural." Under her leadership, the coalition adopted an open access model every participating country could publish independently, provided all raw data remained in the shared repository. The system was intended to prevent secrecy, but soon revealed the complexity of coordinating so many agencies with overlapping priorities. In February 2026, the first peer-reviewed papers appeared in Nature Astronomy, Science Advances, and the Astrophysical Journal Letters. Each focused on a different aspect of the encounter. The ESA team analysed magnetotail perturbations, concluding that a transient plasma loop indeed formed behind Mars and persisted for at least 12 hours. They modelled it as a self-reinforcing standing wave produced by ionized carbon chains in the comet's tail. Meanwhile, NASA's plasma physics group proposed a competing explanation involving Alfvén waves oscillations along the planet's magnetic field lines triggered by charged debris. Neither model could reproduce the resonance harmonics detected by MAVEN, leaving the central mystery unresolved. Across the Pacific, Japan's Subaru Telescope Group published a high-resolution optical study of the swarm fragments, identifying unusual polarization signatures that implied mirror-smooth surfaces. Laboratory replication suggested vitrified silicates or glassy carbon materials requiring temperatures exceeding 1,500 degrees Celsius. "It may have been flash melted during its interaction with Mars," wrote lead author Masato Ishiguro. That implied the object had absorbed and released enormous amounts of energy in a short time, yet no corresponding thermal emission had been recorded. The Chinese Academy of Sciences contributed a detailed infrared analysis using data from the Tianwen-1 orbiter. Their report confirmed trace detections of metallic elements, iron, nickel, and cobalt, consistent with refractory inclusions in primitive meteorites. However, the ratios differed sharply from known solar system compositions. The nickel-to-iron ratio, in particular, was nearly twice the cosmic average. "This is unequivocally material from another stellar nursery," said Dr. Liu Zhen of the National Space Science Center. His claim was met with cautious endorsement from Western peers, marking one of the few times Chinese and American planetary scientists appeared together on the same stage. Behind the public collaboration, however, tensions simmered. Internal emails later leaked to The Guardian showed disagreements over data, timing, and authorship. Some agencies argued that the 8.42 GHz emission data should remain classified until fully understood. Others insisted transparency was vital to maintain credibility. In one exchange, a senior NASA administrator warned of premature interpretations that could fuel speculation. The ESA countered by reminding partners of the open data clause. In the end, the signal files were released unchanged, though without official commentary. The public reaction was immediate. Online forums filled with animated debates about natural mazes, interstellar plasma phenomena, and exotic chemistry. Amateur astronomers replayed archived data and discovered faint harmonics previously overlooked. The result was a crowdsourced science movement. Citizen analysts uploading frequency maps, comparing orbital mechanics, and cross-referencing instrument logs. For the first time, an interstellar object had become a shared investigation between professionals and the public. Meanwhile, government agencies quietly assessed practical implications. The U.S. National Reconnaissance Office conducted a parallel review, noting that the emission frequency coincided with deep space communication bands used by reconnaissance satellites. European defense ministries commissioned studies on potential interference with radar systems. Though no disruptions were found, the reports acknowledged that 3i Atlas had demonstrated nature's ability to mimic artificial precision. By spring 2026, the Project Atlas archive contained more than 4 petabytes of data, from spectral cubes to telemetry bursts. Researchers noticed patterns transcending disciplines. The carbon ion flux recorded by MAVEN mirrored the brightness oscillations seen from Earth. The radio bursts aligned with optical flickers in the debris field. When plotted together, they formed a multi-band rhythm cosmic choreography, replaying across instruments separated by millions of kilometers. It's as if every sensor was hearing the same song, each in its own language, said Dr. Meach at the April symposium. To preserve the momentum, the coalition approved funding for an automated mission concept, a compact probe capable of intercepting future interstellar objects within months of detection. The design, proposed by JPL under the name Interceptor 1, would rely on solar electric propulsion and a deployable dust collector. If launched in the early 2030 seconds, it could reach an inbound object before perihelion. The proposal received broad support, framed as humanity's next logical step after 3i Atlas, no longer passive observers but active participants in studying visitors from the stars. For now, though, the data from 2025 remained the defining record. In hundreds of terabytes of raw telemetry, the traces of that brief encounter persisted, an archive of pulses, spectra, and silent patterns waiting to be understood. Project Atlas had unified nations, bridged rivalries, and opened an era of interstellar research driven not by competition but by shared curiosity. The debate over magnetization. By the summer of 2026, the discussion surrounding 3i Atlas had crystallized around one extraordinary possibility: that the object might have carried a residual magnetic field before entering the solar system. The idea seemed implausible at first. Comets and asteroids are typically non-magnetic, their minerals demagnetized by billions of years of solar radiation. Yet data from MAVEN and Mars Express pointed to a consistent pattern of electromagnetic coupling too strong to attribute solely to plasma flow. The theory's main proponent was Dr. Luca Ferri, an Italian astrophysicist at Sapienza University in Rome. Ferri had spent months reanalyzing magnetometer readings from the July 2025 flyby. He noticed that the orientation of the pulse's alternating shifts in the B field vector followed a repeating arc pattern consistent with the precession of a dipole. "It behaves like a slowly tumbling bar magnet," he told Nature Physics in an interview. His paper argued that if 3i Atlas originated in a young star system with a strong stellar magnetic field, it might have trapped remnant magnetization in its ferromagnetic inclusions. Those fields, though weak, could survive for eons in interstellar cold. The claim drew sharp responses. Critics noted that spacecraft instruments were not designed to detect interstellar magnetization directly. "We're measuring plasma, not solid rock," countered NASA's Bruce Jakosky. "Magnetic signatures can appear from induced currents in charged dust. You don't need a magnetized comet to produce them." A joint study by the Swedish Institute of Space Physics attempted to replicate Ferry's results using synthetic models. They found that similar harmonics emerged when unmagnetized carbon particles interacted with fluctuating solar wind fields. The conclusion: the data could not prove intrinsic magnetization. Still, something about Ferry's graphs bothered observers. The orientation of the recorded pulses was not random. It shifted with each rotation of the object. When plotted in 3 dimensions, the signal traced a lopsided spiral, as if a fixed internal field was sweeping through space. "If it's induced," Ferry wrote, "it is induced in the same direction every time." In late June, ESA's Planetary Science Division reopened the raw Mars Express telemetry to external teams. A group from Kyoto University discovered faint but recurring phase delays between the magnetic and particle flux data. The lag was constant 0, 3 seconds, implying a source that was both coherent and rotating. "That's not background turbulence," said principal investigator Keiko Mori. "It's structure." Their preprint stopped short of confirming magnetization, but noted an internal moment consistent with a remnant field of microtesla magnitude. The debate reached its peak at the Project Atlas Symposium in Geneva that July. Ferry presented his findings to a packed auditorium, displaying a simulation of 3I Atlas's passage through Mars's magnetotail. In the animation, the object's magnetic dipole generated a wake of twisting plasma filaments identical to those recorded by MAVEN. The resemblance drew gasps from the audience, but when Dr. Jakosky took the stage minutes later, he cautioned that correlation did not equal causation. "A magnetized nucleus would be revolutionary," he said, "but so would a natural plasma resonance capable of imitating one. Both are extraordinary, and both require proof." Outside the hall, journalists sensed history unfolding. Headlines the next morning called it "the Comet with a Heart of Iron." NASA released a measured statement acknowledging that evidence for intrinsic magnetization remains under active investigation. Privately, mission engineers admitted the data were unlike anything they had modeled. By September 2026, several independent teams had weighed in. A group at MIT analyzed the decay of the electromagnetic pulses after the encounter and found that their damping curve fit an exponential consistent with eddy current dissipation in conductive material, essentially energy leaking from a magnetized core. Another team at CNRS in France countered that dust-plasma coupling could produce the same curve under specific conditions. Each dataset could be bent to fit both interpretations, leaving the scientific community divided. Yet an unexpected clue arrived from beyond Mars. The Solar Orbiter mission, operating near Venus's orbit, detected a faint stream of carbon ions matching the chemical signature of the 3I Atlas swarm. Embedded within that stream were tiny fluctuations in magnetic orientation microsignals that repeated every 9 hours, the same rotation period recorded a year earlier. The reading was barely above noise, but it extended the timeline of the anomaly far beyond the initial flyby. "It's like an echo travelling down the solar wind," said Dr. Hamill. "Something is carrying the memory of that field outward." The results reignited Ferry's argument. If the fragments were still emitting weak magnetic oscillations months later, they must have retained some intrinsic field. The data were presented at a closed ESA session in October. No consensus emerged, but few dismissed the possibility outright. By the end of 2026, the debate over magnetization had shifted from skepticism to cautious curiosity. The conservative view held that natural plasma effects could explain everything. The bolder interpretation suggested that 3I Atlas might indeed be the first magnetized interstellar body ever observed, a relic carrying the frozen magnetic fingerprint of its birth star. For now, the instruments had fallen silent, the object far beyond Jupiter's orbit. Yet in the laboratories of Earth, its magnetic whispers continued to echo through equations, hinting that even in the vacuum between suns, memory can survive, the dust that rewrote isotopes. In early 2027, a set of sealed containers arrived at NASA's Johnson Space Center under quiet escort. Inside were minute samples of dust captured by the upper atmosphere of Mars during the 3I Atlas encounter, the same material that Perseverance's instruments had recorded as interstellar rain. The particles, no larger than a few microns, had been extracted from filters aboard the ExoMars Trace Gas Orbiter and returned via a capsule launched months earlier by the joint ESA-NASA Sample Relay Program. To the untrained eye, the dust was indistinguishable from any other micrometeorite residue. But within weeks of analysis, it became clear that this collection did not belong to the solar system. The first results came from the Johnson Isotope Geochemistry Laboratory, led by Dr. Laura Vance. Using secondary ion mass spectrometry, her team found ratios of carbon, oxygen, and silicon isotopes that defied established models. The carbon grains contained up to 7% enrichment in the isotope C13, far above the solar ratio of 1.1%. Even more striking was the oxygen signature, an excess of O18 and a corresponding deficit of O17, producing a line offset from the terrestrial mass fractionation curve by more than 3 sigma. It doesn't match Earth, Mars, or any known meteorite class, Vance told Science in a February 2027 briefing. This dust was born around another star. The isotopic fingerprint resembled that of pre-solar grains found in primitive meteorites. But the combination of heavy oxygen and elevated carbon was unprecedented. The pattern suggested synthesis in a red giant stellar envelope, later reprocessed in a supernova shock front, a rare double inheritance seen in only a handful of interstellar samples from NASA's Stardust mission. "We're looking at material older than the Sun," Vance said, "but somehow it was preserved, unaltered, and then dropped into Mars's atmosphere by a passing visitor." Parallel work at the Max Planck Institute for Chemistry in Mainz examined the same particles under transmission electron microscopy. The images revealed intricate lattice structures, silicate frameworks laced with nanometer-scale metallic veins. These veins were composed of nickel, cobalt, and a trace of palladium arranged in a quasi-periodic pattern. Under polarized light, the grains exhibited a weak birefringence typical of quasicrystals, materials that form ordered but non-repeating atomic structures. Nature can make quasicrystals under extreme conditions, explained materials scientist Dr. Anya Falk. But finding them in interstellar dust implies violent origin shock pressures exceeding 5 gigapascals. When the isotopic and structural data were combined, a picture began to form. 3I Atlas was not simply frozen rock and ice, but an archive of condensed matter forged in another sun's final moments. Its core likely contained glassy carbon, metal silicate alloys, and complex organics, the building blocks of planets that never formed. The discovery reignited philosophical questions about cosmic recycling. Every atom in the sample had travelled between stars for millions of years before colliding briefly with Mars. Yet another surprise awaited in the organics. At the University of Tokyo's Astrobiology Center, mass spectrometrist Ayumi Sato identified long carbon chains containing nitrogen and sulfur in alternating bonds, molecules resembling thioamides, precursors to amino acids. Their isotopic ratios matched those of the inorganic dust, confirming a shared interstellar origin. "They're stable but fragile," Sato said. "It's astonishing they survived entry, even in Mars's thin air." Though no biological implication was claimed, the presence of such molecules in interstellar debris reinforced the idea that complex chemistry is universal. As findings accumulated, Project Atlas convened a closed symposium in Geneva to integrate results. Delegates from 12 laboratories compared isotope graphs projected on a wall-sized screen. The plots converged on a clear conclusion. The material was chemically alien but physically familiar, composed of the same fundamental elements found in Earth's crust, arranged in patterns that spoke of a different history. The consensus paper published that May carried a restrained title, Isotopic and Structural Diversity of Extrastellar Particulate Matter, associated with 3I Atlas. Yet behind the formal language, its implications were staggering. Outside academia, the discovery ignited public fascination. Media outlets dubbed the dust the oldest relic ever held by human hands. Museums requested microscopic replicas. Even space agencies that hadn't participated petitioned for sample access. To manage demand, the Project Atlas board created a digital archive containing high-resolution imagery and isotopic maps. Within days, hobbyists were analysing atomic coordinates as though deciphering messages. The scientific community largely ignored such speculation, but privately many admitted a similar sense of awe. Back in Houston, Vance's team turned to one final test: noble gas analysis. Using a high-precision mass spectrometer, they heated a single grain until it vaporized. The released gases contained neon-2,1 and xenon-129 isotopes in ratios inconsistent with solar irradiation, but compatible with exposure to galactic cosmic rays over tens of millions of years. From that, the team inferred that 3I Atlas had spent at least 60 million years traveling through interstellar space before encountering the solar system. "It's a time capsule," Vance said quietly. "Not just from another star system, but from another era of the galaxy." As 2027 drew to a close, the scientific narrative of 3I Atlas expanded beyond plasma and magnetism into deep cosmic genealogy. Each dust grain was a record of stellar death, molecular birth, and the quiet persistence of matter across eons. What began as a faint speck in a telescope now told a story older than the sun itself. The implications reached far beyond Mars, reminding researchers that interstellar visitors were not mere curiosities. They were archives of cosmic memory drifting between worlds, waiting for someone, somewhere, to notice. The reflection across Earth. By mid-2027, the 3I Atlas data had escaped the confines of scientific journals and entered the public imagination. Newspapers called it the message that wasn't a message, while philosophers described it as a mirror, something that forced humanity to see itself in the chemistry of another sun. Museums from Houston to Tokyo opened exhibitions displaying magnified images of the interstellar grains, each speck glowing like a captured star. Visitors queued for hours to stare at dust older than Earth. For the first time in decades, a cosmic discovery had transcended politics, economics, and ideology. At universities, new interdisciplinary courses appeared almost overnight: interstellar material science, astroethics, philosophy of cosmic origins. Students debated whether 3I Atlas proved that all planets share a single ancestry. In Geneva, where Project Atlas maintained its headquarters, artists and scientists collaborated on an installation titled 60 Million Years of Silence, a holographic simulation that projected the object's long voyage through interstellar space. Visitors walked through a dark chamber where the comet's trajectory shimmered in particles of light. At the exit, a plaque quoted astronomer Carl Sagan, "We are a way for the cosmos to know itself." Religious leaders also weighed in. The Vatican Observatory issued a statement calling 3i Atlas a reminder that creation is larger than any single world. Buddhist scholars in Kyoto compared its endless journey to samsara, the cycle of rebirth. Even traditionally secular institutions adopted poetic language. The Royal Society's annual address concluded, "We have touched a fragment of another dawn." For a brief season, humanity's divisions seemed to blur under a shared sense of cosmic continuity. But within the scientific community, reflection came with unease. The isotopic evidence placed the material's origin somewhere in a stellar nursery roughly 20,000 light-years from Earth. If fragments like 3i Atlas could traverse that distance and still deliver intact organic molecules, what else might travel the same path? Panels convened by NASA and ESA debated planetary protection protocols for future encounters. Should humanity intercept and sample interstellar bodies directly or observe from afar? "We are no longer passive recipients of cosmic visitors," warned Dr. Meach. "We have become participants in the galaxy's circulation of matter." Writers and filmmakers soon seized on the theme. Documentaries blended real data with speculative narration, echoing the tone of the original Discovery videos. A best-selling novel, The Ashes of Another Sun, imagined civilizations tracing their ancestry through dust carried by comets. Streaming platforms flooded with content about cosmic genealogy. The public's fascination lay not in alien life, but in shared substance, the realization that everything, from mountains to skin, was forged from the same stardust now measured in laboratories. At the Geneva headquarters, Project Atlas scientists found themselves fielding invitations to art festivals as often as academic conferences. The organization commissioned composers to translate magnetometer pulses into sound. When performed at the Montreux Festival, the resulting piece, Harmonics of a Passing World, filled an auditorium with rising tones derived from Maven's data. As the final pulse faded, an image of Mars appeared on screen, its atmosphere briefly illuminated by a synthetic aurora created from 3i Atlas telemetry. The audience stood in silence before erupting into applause. For many, it was the first time scientific data had felt like ritual. Meanwhile, philosophers revisited the concept of cosmic solitude. The late physicist Freeman Dyson had once said that life would eventually spread through interstellar debris. Now, that notion seemed less metaphorical. Essays in Scientific American and Aeon proposed that interstellar chemistry itself constituted a kind of distributed memory atoms carrying information about environments long vanished. "We have proof that matter remembers," wrote ethicist Dr. Elena Cruz. "The challenge is deciding how to live with that knowledge." In classrooms, teachers used 3i Atlas to explain not only science but humility. Children built models of the comet using glass beads and iron filings. When shown how its atoms predated the Earth, many responded with the same astonished whisper, "So we're made of this too?" Educational campaigns emphasized that humanity was no longer an isolated phenomenon, but a continuation of cosmic processes. Even governments, typically cautious with grand narratives, adopted the discovery in public messaging about climate and cooperation. "Our planet," read a United Nations statement on Earth Day 2027, "is one temporary harbour in a much older voyage." Yet as admiration grew, so did introspection. Some questioned whether turning a scientific discovery into art risked diluting its meaning. Others feared that the awe surrounding 3i Atlas could eclipse the painstaking evidence supporting it. Project Atlas's internal review reminded collaborators that mystery is not a substitute for measurement. The team doubled down on transparency, releasing terabytes of raw isotope and magnetometer data for open analysis. Universities on 5 continents began processing it, each contributing to what had become the largest collaborative dataset in planetary science. By the end of the year, the comet itself had vanished from telescopes, lost in the black beyond Jupiter's orbit. But its influence lingered everywhere, from policy papers to poetry, from sound installations to textbooks. In an editorial for Nature, Dr. Vance captured the prevailing sentiment. "We did not discover a new world, we discovered the continuity of worlds." Every particle of 3i Atlas tells us that isolation is an illusion. We are already connected chemically, magnetically, historically to the rest of the galaxy. As the last exhibitions closed and the media cycle faded, what remained was quieter, but deeper. A collective awareness that the dust drifting through space was not alien after all. It was kin. And in that recognition, the story of 3i Atlas became less about what it did to Mars, and more about what it revealed about Earth, a small planet, briefly illuminated by the passage of something ancient, reminded once again of where it truly came from. The birth of Interceptor 1. By early 2028, the echoes of 3i Atlas had evolved into action. What began as data and wonder was now a mission. Interceptor 1, humanity's first dedicated probe designed to chase the next interstellar visitor. The proposal, once an ambitious concept sketched on whiteboards at JPL, gained rapid momentum after the Project Atlas Symposium unanimously endorsed it. Within weeks, NASA, ESA, and JAXA pledged funding, with Canada, India, and the UAE offering secondary instruments. The goal was simple but unprecedented to wait in space, ready to launch at a moment's notice and intercept whatever crossed the sun's gravity from beyond. The blueprint came from lessons written in the plasma and dust of 3i Atlas. Every instrument on Interceptor 1 was built to measure what the previous missions could only glimpse: magnetic topology, isotopic composition, and plasma behavior during high-velocity passage. A compact bus, barely the size of a small car, would carry 3 deployable modules: Magnet, Dust Lab, and Echo Array, each capable of operating autonomously. The main craft would remain in solar orbit near Earth L2, constantly scanning for alerts from the Atlas telescope network and new observatories funded specifically for this purpose. Once an interstellar candidate was confirmed, Interceptor 1 would ignite its solar electric engines and chase. Inside NASA's Building 230 inches Pasadena, engineers repurposed ion thruster designs from the DART and Psyche missions. "We've never built a spacecraft whose target doesn't exist yet," joked propulsion lead Sarah Coleman. Her team designed variable thrust engines powered by Hall effect technology that could remain idle for years, then burn continuously for months without refueling. The entire craft would be wrapped in a protective electrostatic shield capable of discharging micrometeorite hits, an innovation born from the plasma disturbances of 3i Atlas near Mars. ESA contributed the Magnet module, a pair of magnetometers mounted on deployable booms that could map magnetic fields to the nanotesla level. Their calibration stemmed directly from Ferri's magnetization debates 2 years earlier. "If another object carries an intrinsic field," Ferri said during testing in Toulouse, "this time we'll know before it leaves." Japan's contribution, Dust Lab, was equally ambitious. The device used aerogel panels, cooled by liquid helium, to capture particles intact at relative speeds, exceeding 50 kilometers per second technology refined from the Hayabusa missions. Once collected, the samples would be sealed in carbon fiber cassettes for potential return to Earth. The final module, Echo Array, came from the University of Cambridge in collaboration with MIT. It was a swarm of thumbnail-sized transmitters that could detach from the main probe and arrange themselves into a kilometer-wide antenna. Operating as a distributed interferometer, the array could detect and triangulate radio emissions as faint as those once recorded from 3I Atlas's tail. "We're turning the spacecraft into a floating observatory," explained project scientist Layla Darden. "If another signal appears, we'll catch it with full coherence." In June 2028, Interceptor 1 passed its preliminary design review. Construction began at NASA's Jet Propulsion Laboratory, with components manufactured across 5 continents. The collaboration represented a new template for planetary science: one mission, global ownership, shared data from day one. Engineers joked that it was the United Nations of propulsion. Funding came not only from space agencies, but from private foundations, including the Breakthrough Initiative, whose founder Yuri Milner called it "our first handshake with the galaxy." As the spacecraft took shape, debate shifted toward its readiness protocol. Statistically, interstellar objects enter the solar system roughly once every decade. That meant the probe could wait years before deployment. To solve this, planners proposed parking Interceptor 1 at the Earth-Sun L2 point with solar panels angled toward constant sunlight. It would remain in hibernation, awakened only by alerts from the Atlas and Vera Rubin observatories. When a new visitor appeared, ground controllers could initiate pursuit within days, a race against time and gravity. In October 2028, a simulation known as Ghost Chase Run tested the entire system. Data from 3I Atlas's 2025 trajectory were replayed into mission software to see if Interceptor 1 could have intercepted it. The result astonished the engineers. The probe's modelled trajectory would have passed within 18,000 kilometers of the comet's nucleus, close enough for direct imaging and sample capture. "It would have been history," said Coleman, "but at least now we're ready for the sequel." While construction advanced, Project Atlas continued curating the archives of 3I Atlas. Machine learning algorithms trained on the data began identifying faint periodicities in archived radio noise patterns similar to those found in plasma wave harmonics. The discovery hinted that the solar system might host a constant trickle of smaller, undetected interstellar fragments. Interceptor 1's onboard sensors were modified accordingly to perform wide-field searches during dormancy, ensuring it would also serve as a sentinel for transient anomalies. The mission captured public imagination once again. Educational campaigns featured holographic models of the spacecraft orbiting between Earth and the Sun, waiting like a coiled spring. Artists designed posters with the tagline, "Next time, we'll meet it face to face." In classrooms, students learned how its thrusters would whisper rather than roar, pushing steadily through the vacuum. Documentaries narrated by familiar voices framed it as humanity's next act of curiosity, a promise not to miss the next messenger of the stars. By December 2028, Interceptor 1 was nearly complete. Its gleaming solar arrays reflected the lights of the assembly bay, while technicians performed final magnetic calibrations on the deployable booms. In the control room, Dr. Meach watched a simulation of the probe gliding toward a theoretical object. 3I Atlas taught us humility, she said softly, but also urgency. The universe won't wait. When the spacecraft rolled out for environmental testing, a small plaque was affixed to its frame. It bore a single inscription, chosen by a unanimous vote of the mission team, for the dust that crossed Mars and reminded us who we are. The second visitor. The alert came quietly, in the early hours of the 14th of March 2029. At the Haleakala Observatory in Maui, Atlas operator Kendra Lau was scanning automated readouts when a faint moving point appeared in the southeastern quadrant. The motion was too slow for a satellite, too fast for a trans-Neptunian object. She cross-checked the second exposure. Same trajectory, same magnitude gain. When the third frame confirmed a hyperbolic orbit, she sent the coordinates to the minor planet center. Within 30 minutes, telescopes in Chile and Arizona had verified the sighting. Humanity had found its fourth interstellar object, provisionally labeled 4I, Hesperus. Its inbound path was steep, plunging toward the ecliptic at more than 60 kilometers per second. Early orbital calculations projected a close pass near Venus by late July, then a near-Earth flyby in August 2029. The projected approach distance, 0.09 AU closer than 3I Atlas, had ever come. What truly caught everyone's attention, however, was its composition. Even at magnitude 20, spectroscopy from the Subaru telescope revealed an unusual combination of absorption features. Carbon dioxide ice bands overlaid with metallic traces, including iron and magnesium. "It's a hybrid of a comet and an asteroid," said Dr. Eleanor Singh, now head of the Project Atlas Rapid Response Division. If 3I Atlas was a messenger of chemistry, this one might be a messenger of structure. The timing seemed uncanny. Interceptor 1, months from launch readiness, was still undergoing environmental testing at JPL. Yet the mission's design specifically anticipated this scenario, a dormant spacecraft waiting for an interstellar alarm. On March 20, NASA issued a go order. By April, the probe would be shipped to Cape Canaveral for final integration atop a Falcon Heavy. The race had begun. At JPL, engineers reprogrammed the trajectory to match Hesperus's projected path. The new object's velocity meant the intercept window was short, 4 months from detection to launch. No mission in history had ever targeted a body discovered so recently. The interceptor team worked in shifts, running thermal simulations, recalibrating sensors, and validating fuel margins. Everything we've learned from 3I Atlas, the dust, the magnetism, the plasma, now comes down to this, Coleman told her crew during a midnight review. If we catch Hesperus, we'll finally see where these travelers come from. While the engineering accelerated, astronomers gathered data. The light curve of 4I Hesperus showed a tumbling rotation every 5.8 hours. It displayed a muted coma, only faintly visible in ultraviolet. Yet radar imaging from Goldstone revealed something unexpected: facets, planes, and sharp edges inconsistent with a purely natural shape. "We think it's fractured," said JPL radar specialist John Giorgini. "It's polygonal, like a broken plate." The discovery triggered memories of 3I Atlas's organized fragment swarm. This time, everyone wanted direct verification. By mid-April, Hesperus had brightened to magnitude 15 and developed a thin dust tail. Observations from ESA's Gaia spacecraft indicated a weak but measurable magnetic anomaly extending several hundred kilometers from its nucleus. The pattern, a rhythmic oscillation with a 9-hour cycle, sent a ripple through the Project Atlas network. It was the same periodicity once recorded from 3I Atlas's 8.42 GHz emission. "We are witnessing resonance," Ferry declared during a Geneva briefing. "Different object, same frequency family." On April 28, Interceptor 1 launched under clear skies, ascending on pillars of flame that bent over the Atlantic. The live feed showed technicians in the Geneva Control Center clapping silently, eyes wet with relief. "We are no longer waiting," said Dr. Meach over the broadcast. "We are pursuing." After separation, the probe unfurled its solar arrays and began charging its ion engines. Within 48 hours, it was en route to intercept the predicted path of 4 Hesperus, near Venus's orbit. As the object neared the inner solar system, its behavior grew stranger. The coma brightened in pulses, discrete surges spaced precisely 1 Earth day apart. The spectral profile during each pulse shifted toward the blue, as if charged particles were accelerating along magnetic lines. MAVEN and Solar Orbiter both detected correlated fluctuations in the solar wind, faint ripples that seemed to echo Hesperus's rhythm. "This isn't passive," said ESA physicist Jean-Yves Chauffret. "It's interacting with the heliosphere in real time." By June, Interceptor 1 had reached cruising speed, its ion thrusters glowing faintly electric blue. The spacecraft maintained constant radio contact through NASA's Deep Space Network, transmitting streams of diagnostic telemetry. Its echo array began low-gain listening even before arrival, searching for the telltale 8.42 GHz line. Nothing emerged until June 24, when a faint tone appeared just above background noise. It rose slowly, stabilized, and then faded. 3 ground stations confirmed detection. The same frequency, the same modulation pattern. The odds of coincidence were nearly 0. For the Project Atlas scientists, the implication was chilling and exhilarating. 2 interstellar objects, separated by years and trajectories, each singing the same spectral song. "We are beginning to suspect these are not random relics," Singh told Nature. "They might belong to a population fragments of a larger structure or event beyond our solar neighborhood." As July approached, Interceptor 1 prepared for close pass. The probe's onboard cameras calibrated against the glare of the sun, its dust collector panels deployed. The world watched live streams from mission control as countdown timers flickered across giant screens. Somewhere in the darkness ahead, Hesperus was waiting another traveler from the deep, carrying its own archive of memory, perhaps whispering the same ancient rhythm that once brushed against Mars. At 2:17 UTC on July 30, telemetry confirmed first visual acquisition. The object filled the probe's field of view, an irregular, metallic grey body scarred with fractures and reflecting sunlight in pulses. The sensors registered faint magnetic surges. Then, for the first time, Echo Array recorded a direct broadband emission short, structured, repeating, at exact harmonic intervals of 33 minutes, the same pattern that had haunted every dataset since 3I Atlas. And just before the signal peaked, every instrument aboard Interceptor 1 momentarily froze. The feed to Earth went silent for 6.4 seconds, a blackout too brief for failure, too long for interference. When transmission resumed, the data stream showed no damage, no explanation. Only a single anomalous frame appeared, captured by the main camera. A flash of reflected light shaped like a spiral, vanishing into darkness. The silence in the data. The first few hours after the Interceptor 1 blackout were pure confusion. At NASA's Jet Propulsion Laboratory, every console in the Mission Operations Center froze midstream. Rows of engineers stared at telemetry feeds that had abruptly stopped updating. 6.4 seconds of total silence, no signal, no heartbeat, no carrier wave. "We thought we'd lost the probe," recalled Flight Director Sarah Coleman later. Then everything came back as if nothing happened. The systems rebooted automatically, thrusters resumed nominal output, and all instruments reported green. Yet tucked deep in the returning data packets was something that shouldn't have been there. A single image frame, time-stamped precisely 2 hours 17 minutes and 39 seconds UTC. showing a faint, symmetrical spiral of light near the edge of the field. The spiral was not part of any known optical artifact. It appeared in raw, uncompressed image data before any onboard processing. The telemetry logs showed no cosmic ray hits, no camera saturation, and no star pattern matching its geometry. "It wasn't a lens flare," said imaging specialist Layla Darden. "It was structure coherent, luminous, and three-dimensional." The frame's metadata revealed that it lasted less than 1 millisecond. In the next frame, the field returned to normal. The rough surface of 4I, Hesperus, its faint dust halo, nothing more. Back on Earth, data from the echo array antennas told an even stranger story. The array's radio receivers had recorded a broadband pulse during the blackout, an instantaneous spike across multiple frequencies, peaking exactly at 8.42 GHz. The pulse energy exceeded all previous emissions by 2 orders of magnitude. In the milliseconds after the burst, every antenna element briefly desynchronized, as if hit by a transient magnetic wave. Software logs later revealed checksum errors in memory sectors that had been radiation hardened. "Something external overwhelmed the system," Coleman explained during a closed technical briefing. "Not a malfunction, an input." End quote. Project Atlas convened an emergency panel within 24 hours. Experts from JPL, ESA, and JAXA gathered in Geneva to examine the raw telemetry. Playback of the waveform revealed a sharp onset followed by an exponential decay consistent with an electromagnetic impulse rather than mechanical failure. Yet the signal carried embedded harmonics that repeated every 0.099 seconds, the same frequency spacing seen in the maser-like emissions from both 3I Atlas and Hesperus before. "It's the same fingerprint," said Dr. Eleanor Singh, visibly uneasy. "The same pattern, now directly interacting with our instruments." When Interceptor 1 regained steady communication, engineers initiated a full memory dump. The process took 12 hours, transmitting terabytes of stored telemetry back to Earth. As analysts reconstructed the missing interval, they discovered that the blackout wasn't a total loss of data. The onboard solid-state recorder had continued logging instrument output even while transmission ceased. Inside those 6 seconds was a flurry of sensor activity, magnetometer spikes, plasma density surges, and a brief, impossible acceleration of 0.04 meters per second squared. The probe had moved faster than its engines could account for. ESA's Mars Express and NASA's Solar Orbiter, positioned millions of kilometers away, independently detected a synchronous fluctuation in the solar wind, exactly matching the time of the event. Both spacecraft registered a minor but measurable dip in charged particle density, like a sudden vacuum expanding through the heliosphere. For 30 seconds, the sun's steady output flickered by an amount too small for the naked eye but unmistakable to precision sensors. "The disturbance propagated outward," said plasma physicist Jean-Yves Chauffret. "It wasn't confined to the probe, it was everywhere in its vicinity." As the telemetry poured in, Interceptor 1 continued its flyby. The closest approach occurred at 2:19 UTC, less than 2 minutes after the blackout. High-resolution images showed 4I, Hesperus, as a tumbling object, roughly 700 meters wide, its surface a patchwork of metallic grey facets, interspersed with dark, glassy troughs. Spectral analysis revealed traces of nickel, magnesium, silicate, and unexpected crystalline structures reflecting polarized light. A glowing fissure ran across its equator, exhaling faint jets of ionized carbon. The composition was eerily familiar, a near match to fragments of 3I Atlas. When the dust collection module deployed, its sensors briefly registered elevated magnetic flux before normalizing. By then, the probe had already passed the object's trailing edge, leaving the region of highest activity behind. The remaining hours of the mission were uneventful: stable telemetry, smooth communications, predictable engine burns. Yet the datasets, now under analysis, told a more complicated story. Every onboard clock, including redundant timing systems, showed an offset of exactly 6.4001 seconds relative to ground-based synchronization, the same duration as the blackout itself. "It's as if time itself slipped," one engineer joked nervously. In Geneva, Project Atlas analysts began correlating the data. The pulse detected by Interceptor 1 matched the pattern of radio bursts captured from 3I Atlas 4 years earlier, down to the harmonic ratios. Only one difference stood out. This time, the pulse contained an extra modulation at 33-minute intervals, the precise rhythm that had defined the older object's fading signal. "Whatever these are, they're not independent," said Ferry, now leading the mission's theoretical team. "They're related, maybe fragments of a single interstellar structure scattered long ago." The official preliminary report, released by NASA on the 12th of August 2029, was terse. A transient electromagnetic event of unknown origin occurred during the Interceptor 1 flyby of 4-1 Hesperus. All systems are operational and data integrity is preserved. Further analysis ongoing. Off record, however, the mood was one of astonishment. The probe had not only survived an encounter with an interstellar object, but had recorded a direct physical interaction, a handshake, some called it, between solar and interstellar matter. In the months that followed, the data became the new frontier. Physicists searched for natural explanations: plasma discharges, magnetic reconnection events, induced currents from solar wind gradients. None fit perfectly. The spiral of light caught in that single frame remained unexplained. Some likened it to a shockwave, others a projection of magnetic field lines caught mid-collapse. "It's physics we don't yet have equations for," Darden told reporters. But it's physics, not fantasy. As Interceptor 1 continued its outbound trajectory, the world returned to normal operations. Yet in the quiet of late 2029, a few observatories began to notice subtle fluctuations in deep space radio noise, tiny rhythmic pulses that seemed to echo from far beyond the solar system. The frequency was familiar, 8.42 GHz, repeating with the same harmonic spacing. This time, though, the source was not a comet, nor a probe. It came from the direction of interstellar space itself, where neither 3I Atlas nor Hesperus remained. Something or some process was still resonating out there, answering back. The debate over the resonance. By early 2030, the word resonance had become the shorthand for one of the most baffling astrophysical puzzles in modern history. The 8.42 GHz signal, once a curiosity linked to a single interstellar comet, was now being detected by multiple deep space arrays, each recording the same spectral rhythm from different directions of the sky. What began as a narrow scientific question about plasma physics had evolved into a global debate about the limits of what could be considered natural. At the Jet Propulsion Laboratory, the Interceptor 1 Investigation Board met daily to dissect every second of the flyby data. Engineers reconstructed the probe's memory logs down to individual bit flips, searching for software errors that might have generated false signals. None appeared. "The hardware did exactly what it was designed to do," Coleman reported. "Whatever we saw, the instruments saw too." When a statistical audit confirmed that the waveform's harmonic ratios were identical to those observed from 3I Atlas, matching to within 0.001%, skepticism turned to unease. The probability of coincidence was astronomical. ESA's astrophysics division convened a parallel panel in Darmstadt. Plasma theorists argued that resonance could arise from magnetic reconnection events along interstellar current sheets, vast cosmic circuits threading the galaxy. In that model, interstellar objects like 3I Atlas and Hesperus might act as nodes, amplifying existing electromagnetic oscillations. Their tuning forks, explained Jean-Yves Chauffret, vibrating to the frequency of the galaxy's own current. Others countered that such structures would require electric fields, orders of magnitude stronger than anything observed. The debate filled conference halls from Pasadena to Kyoto. Meanwhile, radio observatories continued to detect faint echoes of the frequency, now designated the Atlas line. The square-kilometre array logged persistent emissions drifting slowly toward lower energy, as though cooling. The source regions were diffuse, spanning several degrees of sky, impossible to localize. China's FAST telescope reported that during certain detections, background hydrogen lines dimmed slightly, implying interference at the atomic level. "We're not hearing a transmitter," said Dr. Liu Zhen. "We're hearing chemistry reorganizing itself." In Geneva, Project Atlas became the nerve center of the debate. Hundreds of researchers pored over terabytes of Interceptor 1 data, trying to connect microscopic dust composition with macroscopic resonance. The breakthrough came from an unlikely source, a graduate student at the University of São Paulo, Ana Ribeiro, who noticed that the harmonic intervals corresponded exactly to electron transition energies in ionized carbon chains C6H- molecules, first identified in the dust of 3I Atlas. "The pattern isn't communication," she wrote in her preprint. "It's physics. These molecules hum when exposed to magnetic fields of a certain strength." Her paper suggested that both interstellar objects and the surrounding plasma had reached the same magnetic conditions, producing synchronized microwave emissions, an interstellar chorus of carbon chemistry. The model fit most of the data. Simulations showed that when carbon chains aligned within rotating magnetic fields, they could amplify radiation near 8.4 GHz through stimulated emission, essentially a natural maser, but one tuned by molecular structure rather than stellar energy. It explained the harmonic ratios, the repeating 33-minute envelope, even the broadband pulse recorded by Interceptor 1. "The galaxy may be full of these," Singh told Nature Physics. "We just never had the sensitivity to hear them before." Not everyone was convinced. A minority of researchers, mainly magnetohydrodynamic specialists, pointed out inconsistencies. The Atlas line emissions showed coherence lengths too long for random molecular alignment. To maintain such stability, the emitting regions would need to be linked across millions of kilometers by a uniform magnetic phase. "That's not chemistry," Ferri argued. "That's structure." In a controversial talk at the 2030 Royal Astronomical Society meeting, he proposed that the resonance represented an ancient galactic relic, a standing electromagnetic wave echoing through interstellar space, occasionally made visible when objects like 3I Atlas passed through its nodes. His model drew applause and skepticism in equal measure. Outside academia, public fascination returned in force. Media outlets called it the heartbeat of the galaxy. Streaming documentaries dramatized the data blackout, the spiral of light, the identical frequencies. Scientists gave interviews emphasizing that no evidence suggested anything artificial, but nuance rarely survived the headlines. Conspiracy forums declared the resonance a reply to humanity's telescopes, while artists composed music based on its harmonic intervals. One orchestral performance in Berlin featured cellos tuned precisely to 8.42 GHz, divided down by powers of 10. The haunting tones filled the hall like the echo of a cosmic pulse. In July, NASA and ESA released the Atlas Consensus Report, a 300-page synthesis authored by 48 institutions. Its conclusion was cautious, but profound. The Atlas line represents a newly recognized class of natural electromagnetic resonance, arising from the interaction between ionized carbon structures and large-scale galactic magnetic fields. Its recurrence across multiple interstellar bodies implies a shared origin or environment. In essence, the universe itself was humming a quiet, ordered frequency hidden within chaos. Yet, even as consensus formed, anomalies persisted. Late-season data from the Deep Space Network revealed that the frequency was drifting downward by 1 Hz per week, an unexplained decay consistent across all stations. Extrapolated backward, the drift began the day of the interceptor, one blackout. Whatever happened during those 6 seconds didn't end with the flyby, Darden observed during a closed meeting. It started something. By autumn 2030, the world's telescopes turned toward the direction of the drift, tracing the fading tone as it moved beyond the heliosphere. The signal was weakening, but its rhythm held. Every 33 minutes, a faint harmonic pulse crossed the detectors, steady as breath. Whether it was chemistry, magnetism, or something else entirely, the resonance had become the galaxy's newest mystery. A reminder that even in the vacuum between stars, order can emerge, sing, and slowly fade into silence. The map beneath the noise. By early 2031, the Atlas line had faded beyond most ground-based receivers, yet not beyond curiosity. The last clear detections came from the Voyager 2 probe, still transmitting weekly from beyond 130 astronomical units. Its antiquated radio instruments, recalibrated by Project Atlas engineers, picked up the 8.42 GHz resonance, faint but regular like a pulse beating in the dark. Analysts at the European Space Operations Centre converted the readings into spectrograms. When stacked over several weeks, a pattern emerged, a gentle sign-like drift that curved through frequency and time. When plotted in 3 dimensions, the curve resolved into a spiral eerily similar to the luminous shape captured by Interceptor 1 during its blackout. The finding electrified the Atlas community. "It's not random," said Dr. Eleanor Singh during a press call. "It's geometry. The frequency isn't just fading, it's describing a path." Soon, every major radio observatory joined in. Data from NASA's Deep Space Network, China's FAST, and the Square Kilometre Array were combined into a single composite dataset covering the entire 8.3–8.5 GHz range. The faint oscillations lined up across hemispheres, producing interference fringes that hinted at spatial structure like the nodes and antinodes of a colossal standing wave. In Geneva, the Project Atlas analysis team created a global frequency map. When they overlaid the resonant regions onto galactic magnetic field models derived from Planck satellite data, the alignment was uncanny. The strongest detections fell along a vast filament of magnetized plasma stretching from the Orion Arm towards Sagittarius, an interstellar current sheet tens of light-years across. The 3I Atlas and 4I Hesperus trajectories had both crossed that same filament. "They came from the same road," Ferry remarked, "and the road itself is singing." The discovery reframed the entire phenomenon. What scientists had been treating as isolated events now looked like intersections with a larger, unseen system, a galactic magnetic lattice whose resonances became audible only when something disturbed it. The Atlas line, in that view, was the universe's low-frequency murmur, the sound of charged dust, carbon molecules, and magnetic fields vibrating in coherence. The standing wave model predicted that the frequency should drift downward as the solar system moved away from a nodal region. The observed 1 Hz per week decay matched perfectly. In March, ESA convened an extraordinary session at Darmstadt to present the magnetic filament hypothesis. The presentation, delivered jointly by Singh and Ferri, displayed a simulation of the Milky Way's spiral arms, overlaid with faint blue lines representing magnetic filaments. Where those lines intersected, luminous points pulsed at intervals of 33 minutes, the predicted resonance nodes. The model suggested that these nodes could span entire star systems, occasionally concentrating matter along their paths. If this is correct, Singh said, then interstellar objects aren't random wanderers. They're passengers on magnetic rivers that thread the galaxy. The idea was radical, yet elegantly testable. If the Atlas line truly traced a magnetic structure, the frequency should rise again when Earth crossed another node. To prepare, Project Atlas commissioned a new listening network, 20 synchronized dishes distributed from Hawaii to Namibia, forming what they called the resonance array. Each antenna was tuned exclusively to 8.42 GHz, operating in cryogenic isolation to eliminate noise. The array came online in May 2031. For weeks, it heard nothing but the faint hiss of cosmic background. Then, on June 2, a single harmonic burst appeared stronger than any since the interceptor event. It lasted 4 minutes, modulated in precisely the same 33-minute envelope. The signal originated not from deep space, but from the direction of the heliopause, the boundary where solar wind meets interstellar medium. It's bouncing off the edge of our own bubble, Darden said. We're hearing the interface vibrate. The amplitude oscillations matched the shape of the solar magnetic tail trailing behind the sun's motion through the galaxy. For the first time, humanity was listening to its own magnetic footprint interacting with the greater galactic field. The implications were immense. If the heliosphere itself could resonate within this lattice, then every star might be part of the same hidden orchestra, a network of magnetic membranes singing at different harmonics. Astronomers dubbed it the Galactic Resonance Map, a conceptual diagram rather than a literal image, a living model of the Milky Way not by starlight, but by vibration. Its scale dwarfed imagination filaments tens of light years wide, pulses rippling over centuries, each node a meeting of cosmic tides. By late 2031, the map had expanded through data contributed by Voyager 2, Solar Orbiter, and the Resonance Array. Patterns converged into arcs and loops, resembling the spiral arms of the galaxy themselves, as if magnetism and matter had co-evolved into the same architecture. In academic circles, debates shifted from what caused the resonance to what maintained it. Some proposed a feedback mechanism between cosmic rays and molecular clouds. Others suggested that rotating galactic fields naturally sustain oscillations, their energy drawn from differential rotation of the Milky Way's core. Whatever the cause, it appeared stable, an enduring heartbeat running beneath the noise of stars. In October, as the last data of the observing season arrived, an unexpected modulation appeared in the resonance. The frequency wavered briefly, forming a secondary tone 30 Hz lower. When analysts converted the dual frequency into a spectrogram, the pattern mirrored the spiral recorded by Interceptor 1 year earlier. The coincidence was perfect in scale and proportion. "It's a signature," Singh whispered as the image resolved. The same geometry, now written across light years. For the first time, scientists began to speak of the resonance not merely as a phenomenon, but as a structure, an invisible architecture underpinning the galaxy's magnetic skeleton. The dust of 3I Atlas, the signals from Hesperus, even the 6-second silence of Interceptor 1 had all been fragments of a larger map, one that no one had known existed. And somewhere out there, beyond the edge of the sun's reach, that map was still vibrating, patient and precise, as if waiting for the next traveller to cross its path. The shift in the field. By mid-2032, the resonance array had become the most sensitive instrument ever built for a single frequency. 2 years of continuous listening produced a library of faint pulses, each a trace of the Atlas line now extending beyond the heliosphere. Then, in May, a new pattern appeared. The emissions no longer arrived from one direction. They were coming from all around the solar system, as if the field itself were folding inward. The sun's magnetotail, once silent, began to hum with the same 8.42 GHz tone. At first, scientists suspected local interference. The frequency matched none of the array's internal electronics, but cosmic sources rarely surrounded a detector. Yet every observatory, from the Deep Space Network to FAST, recorded the same isotropic pattern. The wavefronts arrived in perfect phase, their timing synchronized across Earth within milliseconds. "It's not just passing through us anymore," Singh told reporters. "It's interacting with us." Within weeks, instruments aboard Solar Orbiter and Parker Solar Probe registered subtle increases in ambient magnetic pressure near the heliopause. Voyager 2's telemetry showed fluctuating current densities where none should exist. The field wasn't steady, it was oscillating, contracting fractionally every 33 minutes before relaxing again. To Ferry, the meaning was unmistakable. The galactic lattice was moving, and the solar system was drifting toward one of its nodes. Project Atlas declared a Level 1 observation campaign. All antennas retuned, all planetary probes switched to high gain. The goal was to chart the shape of the approaching field before it enveloped the heliosphere. Simulations suggested a vast magnetic eddy, thousands of astronomical units wide, slowly rotating like the eye of a storm. The resonance wasn't random, it was the rhythm of the eddy's rotation. As the sun's own field touched its edge, interference patterns bloomed, producing the isotropic glow now surrounding Earth. Governments issued no public statements, though satellite operators quietly updated shielding protocols. For ordinary citizens, the phenomenon was invisible. No lights in the sky, no change in the weather. Only radio astronomers heard the deep, steady hum underlying their instruments. In Geneva, the Atlas Command Center pulsed with quiet urgency. "If this is a true magnetic convergence," Darden said during the June briefing, "we're about to learn what happens when two cosmic fields collide." In late July, Voyager 2 transmitted its final burst of data before power depletion. The last packets contained a sharp uptick in charged particle density and an unexplained rotation of the probe's magnetometer boom by 0.03 degrees, too deliberate for random drift. Hours later, the signal faded into static. On Earth, the resonance array recorded a corresponding spike, a single, clean harmonic that split into 3 tones spaced exactly 1/3 of an octave apart. When overlaid on previous recordings, the triad completed the spiral pattern seen in both Interceptor 1 imagery and the galactic map. "It's the same signature, now in full," Singh whispered. By September 2032, the heliospheric boundary glowed faintly in ultraviolet as measured by New Horizons. The Atlas line's amplitude peaked, then began a slow decline. The sun's magnetic field absorbed the oscillation, damping it into a low murmur. The convergence had passed, leaving behind subtle shifts in solar wind orientation that instruments continued to track for months. "It brushed us," Ferry said in his final briefing, "like a tide touching shore." The phenomenon became known as the heliospheric resonance event, a cosmic handshake between the sun's bubble and the galactic current sheet. No catastrophic effects, no visible spectacle, only the quiet proof that magnetic structures on scales of light years could ripple across the void and briefly align with ours. When the Atlas network finally fell silent, the frequency stabilized at 8.41997 GHz, a faint echo buried in background noise. Years later, the data would show that the event had slightly reoriented the solar magnetic axis by less than a fraction of a degree, but measurable. The resonance had left a trace, a gentle reminder that the sun, the planets, and the dust between them were not isolated at all, but participants in the slow breathing of the galaxy. The memory of dust. In the spring of 2035, long after the hum had faded, the world marked the 10th anniversary of 3I Atlas's discovery. The Project Atlas headquarters in Geneva had transformed into a museum, a living archive of the era when humanity first realized the galaxy was not silent. Beneath glass, displays, the original aerogel tiles from Interceptor 1 glittered faintly under sterile light. Visitors leaned close to see the microscopic scars left by interstellar grains, tiny craters that had once carried isotopes from another sun. Dr. Eleanor Singh, older now, guided a group of students past the exhibits. On the wall, a looping projection showed the waveform that had haunted astronomers for a decade. The 8.42 GHz Atlas line drifting slowly downward like the heartbeat of a dying star. "It's still out there," she told them quietly, "just too faint for us to hear." The students stood in silence, watching the line fade to static. Elsewhere, the resonance array had been decommissioned. Its dishes lay dormant under the Namibian sky, their metal surfaces reflecting constellations that had not changed in millennia. On calm nights, maintenance workers claimed they could still sense a vibration through the ground, a low tremor that came and went every half hour. Scientists dismissed it as wind harmonics, but those who had listened during the peak years recognized the rhythm instantly. The field might have moved on, but its echo lingered like memory in metal. The Interceptor 1 probe remained functional, drifting beyond Neptune's orbit. Every few months, it transmitted a housekeeping ping, simple telemetry confirming it still lived. One such transmission, recorded in May 2035, contained an anomaly. A brief phase shift in the carrier tone, precisely 1 part in 8 billion, the same fractional difference that separated 8.42 GHz from its decayed value. Engineers called it coincidence. Singh smiled when she read the report and said nothing. The dust recovered from Mars had long since been catalogued, divided among laboratories across the world. Yet every reanalysis seemed to reveal something new. In Tokyo, atomic resolution imaging revealed lattice imperfections arranged in repeating spirals, their pitch matching the geometry of the magnetic filaments mapped years before. In Houston, isotopic dating pushed their origin back another 100 million years beyond the lifetime of the star once thought to have birthed them. The samples were not just relics, they were witnesses, carrying within them the quiet record of galactic tides. Philosophers found in that idea a strange comfort. If matter could remember, then nothing in the universe was truly lost, only transformed. The atoms of 3I Atlas, once forged in a red giant's heart, had drifted across interstellar space, brushed against Mars, and now sat inside human laboratories, part of human thought. "We became their next vessel," wrote ethicist Elena Cruz in her final essay. "The galaxy learns through us as we learn through it." By late summer, the last surviving member of the original Atlas survey team visited Haleakala. The telescope dome, freshly repainted, still faced the same stars that had first revealed the faint, fast-moving dot in 2024. At midnight, The astronomer stood alone by the railing and watched the Milky Way arch across the sky. Somewhere in that glittering river, the magnetic filament still flowed, carrying unknown travellers toward unseen worlds. The hum was gone, but the silence felt different now. Not emptiness, but rest after song. In the Geneva Museum's final gallery, a plaque bore a line carved in brushed titanium. Every atom remembers where it has been. Beneath it, a small glass sphere held a single grain of interstellar dust, dark, irregular, older than the Sunday. No label, no numbers, no explanation. Just the grain itself, suspended in still air, the last tangible trace of 3I Atlas. It gleamed faintly in the light, as though waiting for the next field to find it. And in that shimmer, silent, rhythmic, patient, the story of the first interstellar visitors found its quiet end. In the end, 3I Atlas wasn't just a comet. It was a reminder that the space between stars is not empty, but alive with memory. From the faint pulse over Mars to the silent hum that reached our own sun, its journey traced invisible threads, connecting everything we thought was separate. The dust it carried became our evidence, the resonance our reflection. Long after its trail vanished into the dark, the data it left behind still whispers through our instruments, proof that the universe keeps its own rhythm, patient, intricate, eternal. And though the signals have faded, the questions remain, echoing in the same silence that once concealed it. What else drifts between the stars? What other stories wait, unheard, in the quiet around us? 3I Atlas passed only once, but in its wake, the galaxy itself began to sing.